Hi ladies, let's go ahead and begin our review for Chapter 9. Okay ladies, so let's start with some big concept questions. So what is a significance test? Right, so basically a significance test is your formal procedure for comparing observed data with a claim. And you do this with a hypothesis whose truth we really want to assess. The claim is always a statement about a parameter, so the parameter is either p or it's mu. And a test asks if the sample data gives good evidence against a claim. So I'm going to write that one. If the test asks if the sample data gives good evidence against a claim, against being the key words here. Okay. If we took many random samples and the claim were true, we would rarely get a result like this. That would be a lot of evidence against a claim. So an outcome that would rarely happen if the claim were true is good evidence the claim is not true. So in English, basically what we're trying to find out is if you have a really low probability of this occurring, the null must not be true. Okay, what is a p-value? So this is the probability that measures how well the data and the claim agree. So how well the data and the claim agree. Okay, so this is the probability or numerical measure, if you will, of how strong the sample evidence is. And remember, if your p is low, the hoe got to go. Okay, so let's go on to our next question. When would you claim that the null hypothesis is true? Haha, false. The conclusion, you can never conclude that the null is true. You look for evidence against the null. If you have that, you say that you reject the null. If you can't find evidence against the null, you never say that the null is true. You say you fail to reject. So there is no such thing as the null is true. So if you have your p-value is less than alpha, then you reject your null. And if your p-value is greater than your alpha, you fail to reject. There is no truth, just fail to reject. And remember when you're doing this, when you reject the null, you have evidence for your alternate. Okay, and then this one you don't have evidence of your alternate. Okay. Ooh, what is the significance level? Well, in a shorthand term, your significance level is your alpha, right? So if your p-value is smaller than your alpha, we say that the data is statistically significant at the level of your alpha, right? But basically, it's just your alpha level. Okay. Type 1 and type 2 error. So remember type 1 and type 2. Type 2 fail to reject. So in type 1, you've made the decision to reject the null and you're wrong. Okay, and then type 2 is where you fail to reject and you're wrong. So those are your type 2 and type 1 errors. Okay, and then the next one, the $1,000,000 question. What in the world is that power thing? Okay, So the power of a test is always against a specific alternative. So we're going to say, like, how likely are you to be able to see that this is very different from, that this value is very different from the null? So the power of the test is against a specific alternative is essentially the probability that you will correctly reject the null when you should have correctly rejected the null. So this is essentially the sensitivity of the test, if you will. It's the ability for you to recognize that the null is wrong correctly. That's all power really is. Okay, it wouldn't be statistics if we didn't talk about planning a study and how we do experimentation. So really when you're doing practicalness of trying to come up with these numbers and whatnot, the first thing that you as a researcher or as you as a statistician need to figure out is what kind of significance level are you going to be using? Now, we've been saying a standard of 5%. So in our potato chip example, there's a 5% chance that someone will make, the potato chip producer will make like a type 1 error, something like that. So you want to try to think about what significance level are you going to be comfortable with, how much protection do you really want against a type 1 error, and what kind of percentage of type 1 error are you willing to live with. The next thing that you want to think about is practical importance. Yeah, actual practical stuff. That's nice. So how large of a difference between the hypothesized parameter value and the actual parameter value is really important in real practice. For the potato chip example, if I'm looking at a 3% difference between my good potatoes and my bad potatoes, is that enough? Do I really care about 3%, or would I even care about 1%? But I might care about an 11% difference from my actual and my actual parameter and my hypothesized parameter. So really kind of look at what is that difference. The last thing that we have to consider is what kind of power do you want? How confident do you want to be that in your study being able to detect a difference of the size that you think is important? So if I'm saying that 10% of my potatoes are bad, the truckload's got to go, then maybe I want to test the power of me being able to decide that 20% is very different from the true mean. How often will I be able to assess that? Okay, so a little bit more about planning a study is you want to think about these type 1 and type 2 errors. So remember that your type 1 error is your alpha, and that decreasing the significance level or your alpha level decreases your risk of a type 1 error. So if your alpha goes down, type 1 error goes down. Yay, that's nice. Okay. So, and then if you remember, your type 2 error is your 1 minus your power. So lower power, so when your power is low, right, then you're going to have a greater chance. If your power is low, you have a higher chance probability of type 2 error. So if your power is lower, probably should have done this differently, but your power is lower, the higher your type 2 probability. This makes sense because the more power you have, the less type 1 or type 2 error you're actually going to make. Now, of course, they're opposite to each other. So if I increase my type 1 error, like my threshold for what I'm okay with my type 1 error, my type 2 goes down. If I increase my type 2 error, my type 1 goes down, and vice versa. So the best way to sort of reduce your error, again, is to increase sample size. I'm going to write that here, huge. Increase sample size. Do it. Okay, so if you need a smaller significance level, like an alpha of 1% rather than 5% for some ridiculous reason, you need a larger sample size, right? If you really need a high power, like 99% instead of 90%, you need a larger sample size. So really, at any significance level and desired power, detecting a small difference as opposed to a large difference, that's going to require a larger sample size. So moral of the story here is our best advice for maximizing power of a test is to choose as high of a type 1 error as you're willing to risk and as large of a sample size as you can afford. Okay, so we talked about two main types of tests. We talked about proportions and means. So when we're talking about proportions, what test statistic are we using? When we're doing proportions, it's the Z. So formula is p hat minus the p null divided by null and minus 1 over n square root. Okay, so this is our test statistic for when we're doing proportions. So proportions are Z. So you want to find the p-value by calculating our test statistic Z and then looking at the p-value for that. And remember, it matters if you're doing two sides of a test or greater than or less than. If you're looking at a two-tailed test, like so, if this is what I want, I'm going to have to multiply whatever I get for my p-value by 2. All right, so the state's always the same. We're going to state that we want to test the following hypotheses. We're going to list our null. We're going to list our alternate. We're going to define our parameter in context, and then we're going to give our alpha. When we get to the plan part, we state the name of the test that we're going to do. So in this one, we're talking about a one proportion Z test. Okay, and then we would go into our conditions. So ren, same, independent, we're talking about 10%, and then for n, remember that it's n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So those are our conditions. We use our z-score to get our p-value, and that's what we need to do. On the TI-89, if you'll remember, this is a one prop Z test. I would suggest that you please, oh please, oh please, show me the Z statistic. Like, show me all the math worked out, and then if you want to do your calculator, by all means. But you will lose points if you don't list every single thing that you need to enter in on your calculator. So go for showing me the math and then checking it with your calculator. Okay. And then two-sided test, we double our p-value. Remember to always, in the plan part, kind of draw a picture of what you're going to do. I would even draw it in the state, just like list it. I want this. That would be a two-sided, or this would be a greater than, or this would be a less than. Just really ugly drawing. Fabulous. We love it. Okay, ladies, so the mean, again, our test statistic is a t. So our t is x bar minus our mu divided by our standard deviation divided by square root of n. And this is the test statistic that we're going to use. So you can read what I wrote there, so I'll make it make more sense. There we go. So remember that this is a t. The name of this is going to be a one proportion t test. Okay, we also talked about a paired t test. This would be when you have two different values and you're looking for the mu difference. Okay, so this we have one sample. This one we have two sample sets of data. And we're looking for the difference. And remember that you state your mu in terms of your difference on a paired t-test. Okay, so t-test, paired t-test, those are the names we're talking about. The conditions will be the same, randomness, 10%, And then the normal is going to be our central limit theorem, so n has to be greater than 30. If for some reason it's less than 30, we hope that it's greater than 15, because then we can have either a skew or outliers. Okay, so one or the other is fine. And then if n is less than 30, you can have neither outliers nor strong skew. Sorry, it's tough life. That's the way it is. And then remember, on your TI-89, we're talking about a t-test. Okay, so that's about our unit. A couple of important points to talk about, things that the AP exam loves to throw at you. The idea of practical importance. Statistical significance is not the same thing as practical importance per se. So let's look at this example. Suppose that a large school district implemented a new math curriculum for the current school year. To see if the new curriculum is effective, the district randomly selects 500 students and compares their scores on a standardized test after the curriculum change with their scores on the same test before the curriculum change. The mean improvement was x bar equals 0.9 with a standard deviation of 12. Calculate the test statistic and p-value for a test of difference is 0 versus the alternate, the difference is less than 0. Are the test results significant at the 5% level? And then can we conclude that the new curriculum is the cause of the apparent increase of the scores? Okay, so here we go. If I were going to do the test statistic, then I'll do it down here. So I would do my t 0.9 minus 0. That's my little there. 12 divided by, we said 500. 500 students. When I do that, I get 1.68. So if I find the p-value for that, so the p-value for that is 0.047. Okay, so that is lower than my 5% level. So since the p-value is less than my alpha of 0.05, the results are significant at the 5% level. The improvement was larger than what we would expect to happen by chance. So all that is true. Great. Woohoo! Except for, let's think about this in real life. Can we conclude that the new curriculum is the cause of the apparent increase in the scores? Not at all. We didn't go through any sort of, we can't conclude anything really. There's no control group for comparison. There's no randomized assignment of treatments. If we don't have these things, we can't necessarily draw a conclusion. So it's important to note that although you can find something to be statistically significant, is it worth your time to look at this? Have you conducted your study well? Okay, so other important points. So what I just talked about in considering practical importance, we'll call that important point number 1. So important point number 2, I would say, is really don't ignore the lack of significance in studies. So just because a study says it's something that the data isn't statistically significant doesn't necessarily mean that it's a worthwhile study or that it's not something that we can learn from. So the study that recently came out about correlation but not causation linked to red meat and colon cancer. This is a really important study, one that we should all look at thoroughly. But, the data was not statistically significant. Does that mean that it's not a problem to eat red meat all the time? I don't know. But is this something that should be looked at and studied more? Yes. So we can learn a lot from studies that may or may not have statistical significance. Okay, point number 3, I would say, is that statistical inference is not valid for all sets of data. If you have a really terribly designed survey or experiment, guess what? You can't draw conclusions from it. Even if you have this is statistically significantly different data. You know what? If you have bad design, you can't draw effects from that. So make sure that when you're designing experiments, you're thinking about how the data are actually produced. Okay, so that's enough for weird things to think about for the AP exam. Now what I would love for you ladies to do is to work on your online quiz and your Stride course. If you have any questions, feel free to email me.